I'm Ethan. Today I'm going to be presenting a 2025 paper that compares two ways that we find memory bugs in C and C++, which are fuzzing and static analysis. So I'm not going to be reading the paper straight at you or kind of go through every experiment that they do, but I'm mainly going to be focusing on the big ideas they convey. So what each method is good at, what each method kind of tends to miss, and what a good workflow would look like if you're kind of working on a real project using these. So one small note, this is all kind of in context of memory and safety, so we're going to be kind of mentioning stuff like out-of-bounds access, use after free, and similar bugs that might show up a lot in low-level coding. So kind of a quick motivation for why we use these tools. A lot of memory bugs in C and C++ are a big problem because the language, it trusts the programmer to deal with like raw pointers, memory management. And while great, it gives a lot of flexibility. You can write efficient code. It also means it's a lot easier to write unsafe code. So, big reason that we care about these, especially catching early as possible, is that they can lead to vulnerabilities down the line, especially if you're writing a parser or an image library, or just libraries in general. A lot of other code is going to be using these libraries. So if you introduce memory issues, they will also have issues. So even if even if your app is safe in terms of writing code, a lot of the dependencies are gonna be introducing warnings elsewhere. So another way to kind of look at this is finding these bugs isn't necessarily about the security. It's more building up a foundation and ensuring that everybody else is not going to be dealing with problems that you created. So, like if you ever had a crash that disappears when you use a debugger or only works on one machine, that's the kind of stuff that memory corruption can cause. So, if you picture like a big parser that takes in untrusted input, one mistake in bounds can lead to like a memory bug, and that can range from either causing a crash, it can leak data, or just an entire compromise. So here's kind of the mental model you're going to want to have for this talk. Fuzzing and static analysis are just two completely different ways of looking at software and trying to find these bugs. So fuzzing is kind of like stress testing the program. You're making inputs, you're running the program, you're just trying to watch if the program is failing from these inputs, and if it does, and you get a failure, that's great because you can go down that failure and try and find other failures. So one limitation of fuzzing though is that it's kind of, and while it seems a bit obvious, but it only finds what it's able to reach. So if your inputs aren't actually getting through like the parsing and the validation of the program, it's never actually able to touch that vulnerable code that it's trying to find. So static analysis, on the other hand, it's kind of like taking a look at the code and you're just trying to reason like, hey, what could go wrong? You're never actually executing it. So since it's doing this through pattern matching, like it has these examples of hey, this kind of pattern causes this vulnerability in this group. It's more of an approximation, right? So you might be getting warnings that they say they're important, and they might actually be correct technically, but they're not exploitable at all. So in summary, fuzzing, that's giving strong, more like deterministic evidence when you get a crash, while as like static analysis, it's more of like a macro look at it, right? So, the outputs there aren't going to be necessarily 100% trustworthy. And both can go wrong in different ways. Fuzzing, might never actually reach the problem or the crash, while as static analysis, it might just it's going to give you so much output or warnings. It can be hard to filter out what you want to look for. So, if you had to kind of pick one kind of signal that you're wanting to believe in, like what would you rather have, like a crashing input that works, or like a static warning that might be a problem? Because one, you're getting a lot more of the other, but the other, you might be missing out on some warnings. Right, so these are so different. How are you supposed to compare these, right? So what they did is they took 13 different fuzzers and 5 static analyzers and tested them on just a bunch of different common vulnerabilities known, and compared what was missed, what was found in coverage. So that was their main method of validation and comparison. So kind of going into the historical context, though, static analysis became popular initially, kind of like as a pull request check, because it's something you can like efficiently and quickly run every time the code changes, right? So you're just making sure that you can quickly say, hey, there's not any outlying or crazy vulnerabilities that we're going to be merging. So with fuzzing, on the other hand, that took off a lot more, though, because with fuzzing, it can be long running. You can kind of have it you can leave it running at night, and the longer that you have it running, the better it gets, because it's able to find better seeds and expand upon those. So in practice, these tools kind of evolved and moved around different like rhythms. So static analysis, that's more like the fast feedback. You're going to be getting quick results, while fuzzing, that's like the background long-term thing that's run. The big reason, though, that there is any debate about using one or the other is that they're making completely different artifacts, right? So like fuzzing is giving you like a crashing input, whereas static, that's just giving you a straight up warning, and a lot of warnings at that typically. So it's kind of hard to compare them directly, but there's just no point to debate anything. The paper, however, frames it around 4 simple questions, right? So how much are they finding? How much are they overlapping? But also what kind of bugs they hit, and what the overhead of both look like. So overall, it's the same goal, just different like pros and cons for either or. So now, one important thing to kind of point out here, before I talk about results, you gotta know like what does it actually mean to find a vulnerability. So, of course, with fuzzing, you're executing the program. If the program crashes or hits a bug, that's very deterministic. You're able to reproduce it. You can debug it. You can kind of make a test case around it. Static analysis, though, you don't get that runtime proof. You just get a straight up report, and it's just gonna say like, hey, this looks like maybe out of bounds access, maybe use after free, and then the user itself is forced to have to interpret it. They're kind of the filter. So, in a sense, though, the paper's premise is kind of just like, hey, we're not going to pretend these are the same, of course, but we're still going to ask, like, do these different techniques find the same bugs? Do they find different bugs? What's the kind of overhead for both of them? And that is the right question to ask here, especially in this context. Coverage on things that you can't really take action on or mitigate, doesn't really help anything. And for static, a hit is just like, hey, did the tool point you kind of at the right type of issue, or like in the right neighborhood, and then like the user is able to kind of go from there to figure it out themselves. Right, so this slide here is more about the kind of the real world results, and what the paper did is they took a look at security critical kind of like open source projects, and they were going through the CI pipelines, right, or continuous integration, and looking for signs of fuzzing or using static analysis. So these numbers aren't from the benchmark, and the idea is you're not really you're not supposed to worry about the numbers. That's not the point. The point is, in the real world, no one's sitting there thinking, hey, fuzzing versus static, should I use one or the other? Most projects are going to use one or the other anyways, and a lot of projects are just going to use neither. Which is a little scary when you think about protecting user data. But with that added moral there, it's kind of a given for people who are serious about security and actually care about it. They're gonna pick both. And of course, they both have their own blind spots they don't find, but this slide kind of sets up that sort of overview. And it's normal for like longer term projects, of course, to combine techniques. There's more at stake, and the paper's kind of main results are going through why it makes sense to combine these techniques. So why wouldn't everyone do both? It's usually just cost. Out team allocation to do this. The time is a valuable resource. A lot of people just we'll just decide on one. Right. So yep. Just switching over just to the main result here. Of course, yeah. Fuzzing and static analysis, they're not going to have the same cover the same territory. Bugs fuzzing will tend to find, static analysis won't, and vice versa, right? So there's the third region here that is kind of the worrisome part, is when both have the same blind spot, at least for certain bugs, right? And that doesn't mean that you shouldn't use fuzzing or static just because there is that blind spot. It just means you're either going to have to get deeper kind of access for the fuzzing, be able to reach different branches, or model the static analysis better, or just configure it differently. And sometimes you might just have to use an entirely other method entirely. So that's what the paper kind of pushes here. They said that these are complementary, and it's just mainly describing the fact that the blind spots are different for both. Conceptually, it's kind of just like, you have two different sensors on one system. Each is going to be missing a different kind of failure, and that's the theme for the rest of this, right? So what are those blind spots going to look like? And apologies for the audio change. I had to move to a different area. So, let's kind of look at the biggest limitation of fuzzing itself, which is the reachability. And if a program is required to have a certain input format, such as like a checksum or a compression stream, just randomly mutating a byte, that's going to take forever, right? It's going to be failing before ever actually getting through any gates. And if they do, and it's a validated input, there still might be a ton of conditions past those, right? The success of fuzzing kind of depends on, like I was saying, those gates, right? There's different techniques to mitigate this, kind of like a harness. Those are important because they give you a function to fuzz. Seeds, those are important because you have you're given like a starting point, and that's something that's kind of gotten you through a lot of the gates per se in the past. So that definitely speeds it up the process quite a bit. And then you have also dictionaries, and those is kind of it's giving the fuzzer a guideline on what the input format is. And that's kind of why people say fuzzing is really powerful, but also really easy to do badly, because if you fuzz a binary and you don't have a harness, you don't have seeds, it can give you nothing. But if you put in the work, put in the time, it could go well. It can be super powerful. It'll have guidelines to go down. And so it's more of a search problem, if anything. if the search space is super huge, a lot of the inputs die, you're going to want to reduce just the map, or just the space in general. And that's why it's continuous. That's why it's a long running thing, because you're letting the search run long enough that you get lucky, you get the input format, and then it kind of just it builds off of itself. So a bit of an example. Imagine you have a specific file format and you have a specific header, right? And you need to meet that header to get past kind of any code and be able to that itself is the gate. You have a version length, kind of it also has a checksum. Random bytes are just going to die right away. They're just going to be they're going to be taking a ridiculous amount of time, and then once you get that seed, it's just going to be getting deeper and deeper and deeper. It's not going to face plant right away. And it might be obvious, but the padlocks in this visual here is kind of just it's the gates, and it's just like it represents the time that it needs to be able to explore and get deeper until it actually reaches the bug. So static analysis now is kind of the opposite. It's able to look at the actual paths of the code itself that fuzzing is never going to look at, and that's great and it is great, but it's more of a pain just to actually deal with the output produced from it. Most developers, they have a limited amount of attention to delegate. If they're given a tool and it's just a ridiculous amount of output, a lot of people are just going to ignore it. Or if you don't, you're going to have to spend a ridiculous amount of time making it work. So, a good static analysis process is more so just figuring out how to, set it up and enable it in the right way, and how to reduce as much false positives as possible. You're gonna have to prioritize things. Actually integrating it into the code review can be difficult, especially setting up rules. So those are all essential for being optimal with that tool. And the message of the paper and what that tries to convey is that static analysis, it's able to contribute to coverage, definitely, in kind of I would say more an absolute sense, but you should still kind of, help out and mitigate the errors and the workflow using it is kind of the bigger cost. It's kind of a band-aid to rip off. So this slide is going to be just showing off the overlap within fuzzing, not fuzzing versus static. So it's just looking at kind of diminishing returns. If you have a lot of fuzzers and they have a lot of overlap, you're not going to be wanting to use a lot of those fuzzers. You're just wasting a lot of computation, right? So while you might get a small increase in coverage, just because there are kind of a few fuzzers that are pointing out unique things, you're gonna be using a lot more computation. So sometimes it is smart to use an extra one, but in a lot of the times it's just doesn't make sense. So yeah, like I was talking about with redundancy of this fuzzer overlap, you're just gonna want to use one good fuzzer, and just use the reachability kind of aspect. It's kind of just that's the general theme here, right? Deciding of the tool and how you use the tool, the setup and workflow matters more than just using the a specific tool. So if you are gonna add more fuzzers, you gotta have a good reason for it. And this is just looking at the analyzer side of it. This is different, right? This is not a ton of overlap, and a lot of tools are more specifically finding unique things relative to the fuzzers on the other slide. So the biggest contributor here, as you can see, is analyzer code QL, and you know the the idea is just choosing your tool and the quality of the tool that matters a lot more, as you can see with how much coverage that gets, and well tuning it, taking care of it, making sure that it's on the right track, that will kind of get the majority of what you want. And so, that is kind of just what happens in reality. They don't really run 5 analyzers and read everything. They kind of just standardize it on one main thing, tune it, and then, maybe you're going to have an extra checker, but typically you won't. So, yeah. The slide here is kind of just showing off the trade-off, right? It's just the idea that, hey, like fuzzing, that costs compute, setup, time. You're gonna have to set up, you're gonna need harnesses. You're gonna need it to find seeds. You have to handle crashes. There's something called like deduplicating, and that is just ensuring that certain crashes found aren't correlated to the same bug. Of course, you're gonna have to debug it, right? So, whereas static analysis on the other side, that is, that's time. That's you need. There are so many warnings that come out that either you're gonna want to take care of the output and say, hey, you have this certain rule. You're gonna want to filter it down a lot, and that takes a lot more time than fuzzing. So in real team, it's not just cost. It's not cost and time. It's more so just morale. For static analyzers, if you're looking at all these warnings, if a lot of them are just false positives, a lot of people just tend to kind of stop listening. So moving on, it's kind of just how you would actually deploy it, right? So like, if I'm kind of maintaining like a real project, the static analysis is fitting nicely. Everything's just kind of working well together. Fuzzing's running overnight. It's running continuous. That's kind of how it should be optimally running, right? It's the tools find the issues, the humans fix it, and then the project itself is getting safer, and you're not continually spreading the same class of bugs. And that, of course, like I was saying in the beginning slides, it's better to take care of it earlier on than let it propagate. Like a pull request, static analysis, that's going to be a short amount of time. Continuous fuzzing, hours to days, and those tests that you're running and you catch, you're going to want to keep them, right? If you fix a bug and you run a test and it passes, you're going to want to use that test continuously every time that you are checking for bugs. So, some limitations though. Any benchmark, it's kind of a it's more of a snapshot, right? You have different projects, different inputs. You might have different harnesses, like different qualities, and all of that can kind of change the results, right? So it might not be the same in different scenarios, different setups, and and of course that was in the context of fuzzing, but for static analysis, that itself is more that's more kind of dependent on how you set it up and configure it, rather than just letting it run, right? It's how you interpret the results, and tuning that kind of configuration and how you set it up is it's an art. You're either going to be over tuning it, under tuning it, and that could be impacting the results in the long run. So yeah, the way I'd use this paper is just kind of, I wouldn't use it as just like a tally scoreboard. I would just be saying like, this is how this works. The they're both seeing different things. The costs for each is different. I'm still going to want to use both, and I'm going to want to take care of the setup. So the takeaway here, again, use both. They both find different vulnerabilities. They both kind of um, they both have different pros and cons. But if you just use one strong fuzzer, one strong analyzer, typically you're going to be covering most stuff. And while there is still typically stuff you're going to be missing even when you use both, you're going to have to just refactor. You're going to have to put in the effort to be able to find those. So, I mean, yeah, I mean, they're better together than alone. The challenge is just setting it up in the pipeline, reachability for fuzzing, usability for static, and making sure to keep using the same test that you're making. So, yep, thanks for listening. Yeah.